Hello. Today we will be talking about binary heaps. What are binary heaps? Heaps maintain a partial order on a set of elements. It's easier and more efficient to maintain than a sorted order, but still supports priority queue operations like insert and extract min more efficiently than random order. A heap is a data structure that allows us to represent binary trees without using pointers. We store data in an array. The keys of the array take place of the pointers. Heaps can be reflected as trees. A heap-labeled tree is a binary tree with few rules that must be satisfied. The first rule depends on whether we're talking about max heap or min heap. In max heap, the parent node must dominate the child node by being greater. In a min heap, the parent node must dominate the child node by being smaller. The second rule is that all levels of the tree need to be complete except the last one. The figure on the left is a binary heap because it's all levels are filled except the last. The figure on the right has two incomplete levels and can't be a binary heap.
There are a few steps to implementing a min heap. First, use an array to store the data. Then start storing the data from index 1, not 0. The first element in your array will be your root. Let's call the root's location I. The left child will be at location 2 times I, if available. The right child is at 2 times I plus 1. The parent node of I, if it is not the root, would be I divided by 2. The time complexity for construction of a heap is O n log n, because the first step of constructing a heap is placing all the elements in the array, which would take O of n time. After, we must sort the elements in the binary tree using bubble up or bubble down, which would take O log n time, because worst case, we have to traverse the entire height of the tree. Therefore, the complete time for O log n for n elements would be O n log n. Now that we understand what a binary heap is and how long it takes to create one, we can look at the implementation. One way to create a heap uses a bubble up method. The bubble up method includes two parts, insertion and bubble up. Insertion is used to add a value at the bottom of the heap. Insert then calls the bubble up sorting function on the inserted node. As shown on the diagram below, the node starts as a leaf. It is then compared to its parent. If it is smaller than its parent, the two nodes swap places. This process is repeated until the node is no longer greater than its parent.
Here is our implementation of bubble down. We start with the elements in random order. For bubble down, we start with the root. We compare the root with both of its children. The smallest of the three is swapped into the parent's place. Now we look at the first child. We compare it with its two children, pick the smallest value, and swap. Now on to the second child of the root. Same thing, we swap it with the smallest child. Now the second iteration. Starting with the root again, we swap the same way we did the first time. In this case, the heap is now properly sorted, so we stop. Bubble up generally performs better when the input is in decreasing order because it only has to go through n-1 items, while bubble down goes through n/2 items several times. When the heap is already sorted, however, bubble down only has to compare n/2 items once because the program stops if there has not been any swaps made, while bubble up still goes through n-1 items.